Hello everyone, welcome to day 17 of our machine learning masterclass internship, and I welcome you all to our machine learning internship once again. So in the previous few sessions, I think in the last three sessions we are discussing about algorithms, right? So we have seen a lot of supervised learning algorithms which include both classifications as well as regression based algorithms. We have seen a lot of theory based about it. That's fine. So today we'll be seeing our final part before going into the project, which is going to be our. We also need to complete one of the unsupervised machine learning algorithm. So we'll be seeing about k-means clustering, which is a clustering algorithm in today's session. After that, we have seen a lot of algorithms till now, but there is an important concept which is called as hyperparameter tuning or optimization. So we'll be learning about that. And when we learn about it, we'll be seeing about grid search CV and randomized search CV and cross validation, what it is, etc., and how to apply it. That we'll be covering in today's session. And once we complete that, we'll be stepping on into metrics, which is the model evaluation part. To evaluate how your algorithm works, you need to have some standards, right? So that for comparison purpose, we will be learning about it. And once we complete all this in today's session, it will be covered in this session. Once we complete this, from the next session we are eligible to do projects from start to end. A machine learning project can be comfortably completed with the idea you have or we thought till now is really enough for you to do it very well. So in the next few sessions we will be having projects based on classification, regression and clustering, and then moving towards some of the high-end applications of machine learning. So without any delay, we'll get started with our day 17, and we'll be starting with only one algorithm. So mostly we'll go hands-on for this algorithm, which is going to be k-means clustering algorithm. Once again, this is going to be a clustering algorithm, which is unsupervised learning algorithm. So in unsupervised learning, there will be no label for you, so we'll be having data. So all the data points, the task of the algorithm here is to find the people who are together, or they need to cluster it. For example, see here, see the first image, we are having a scattered population, and in the next they performed clustering to find that I can visually see right here there are few groups only. I can see that 3 groups are available, they are interrelated, so they are divided into clustered population. But when you have a large data set, it's not easily possible for you to just visually see it and find the clusters. So for that we can use the clustering algorithm, and clustering is a type of unsupervised learning concept in which the algorithm processes our data and divide them into clusters or parts. And the thing is here we need to mention how many clusters we require. So you'll be seeing that later. So talking about this particular algorithm, which is called as k-means clustering algorithm, k-means algorithm can divide the given data into the given number of clusters. For example, if you give a bunch of data and ask me to ask this k-means algorithm to divide it into 10 different groups, it will be splitting them into 10. Okay, so it can split this into 10. So if you ask it to split it into 3, it will split it into 3. Okay, based on similar people, they will be grouped together. So how it's done, we'll be seeing that later. So the k number of the clustering that we need to be created, we need to create the k value. So we need to give a value, and there is actually a way to find the best k value. So this k-means clustering algorithm is a centroid based algorithm, which means that there will be a centroid for each clusters you are having. And the main idea is to reduce the distance between the data point and the respective cluster centroid. So what does that mean is, for example, if I have 3 clusters, then for each cluster there will be a centroid available. So based on that centroid, okay, so it will try to fit the centroids and then try to find, if I have a new point, it will try to find which centroid is closer to that point, and that for example, this green color centroid is only closer to my new point, then the new point will be assigned to this particular clustering group, clustered population. So that's how it will do the predictions also. So now if you ask me, that's fine. So he will be passing the k value, so it will be splitting them into that many clusters with centroid. So if you pass a new value, based on the distance between all the centroids, which centroid is nearer, that point will be assigned to that particular centroid population. That's fine now. But talking about the k value, as I told you, we need to provide the k value. Okay, so how to find the best k value? So we will be doing one simple calculation. So it is called as WCSS, which is within cluster sum of squares. Okay, so it's the distance. Okay, I'll tell you what it is against the number of cluster values to figure out the optimal number of cluster value. And this WCSS means the sum, which is the addition of distance of observation from their cluster centroid. For example, imagine we are converting this with 1. Okay, so there the k value is going to be 1 for this data. So for example, 1 means only one centroid for everything. So where will be your centroid is? Your centroid will be here. Okay, somewhat around here, so that every points can be connected. Now the value of WCSS is the sum of these distance. So if you calculate the distance between each point with the centroid, for example, if you have 1000 points here, the 1000 points for each point, what is the distance with the centroid? Okay, so that will be your WCSS value. So like that, if you go with two centroid, then maybe one here and one here. So with that, now what is the task is, so for that centroid, what is their distance in between, and you will be calculating it. If you go with 3 like this, we will be having a centroid here, here and here. For these particular points will be calculated here. Talking about that, imagine if you have only one clusteroid here, okay, the centroid, if it is 1, then the distance, see here, from here, every point will be coming here, so the distance value will be high, WCSS will be very high. But when you keep on going, okay, see here we have 3, okay, so now we have centroid in for each of this cluster, and their distance will be very less with that respective thing. If I have one thing in common, then the distance value will be high. So now since we have centroids nearer to it, the WCSS value will be keep on reducing if you go with increasing the k value or the number of cluster. And what or how we will be finding the best k value is, we will be going with a plot which is called as elbow method. Okay, so what this elbow method is, usually in machine learning, in clustering, if you have a data set, what you will be doing is, you will be calculating this WCSS. You can calculate it from your SQL library. I'll tell you how to do it. That is fine now. So once you have it, what you will be doing is, you will be using a for loop and use this algorithm and fit it. Okay, yesterday we have seen about, or in the previous session we have seen about the KNN, right? So where they used iterative method to change the neighbors. Like that, here we will be set the value of k from 1 to 10, which means first time the cluster will be 1, the centroid will be 1, next time it will be 2, next time it is 3, then so on till 10. And you can see for each of it, they will be calculating the WCSS value, and that will be plotted in a graph. And the x-axis is the number of cluster, and y-axis is the WCSS value, which is within cluster sum of squares. And as I told you earlier, when the cluster value is 1, you can see the value of WCSS is high, because you will be having only one centroid and the distance is going to be very large. Talking about that, when you keep on coming towards this side, when the number of cluster increases, when the number of centroid increases, the distance between like every point will be nearer to some centroid now. So the distance will keep on reducing, so that at a point of time the distance will go down. Okay, the WCSS will be value will keep on decreasing. But in this, how will I find the best fit or the best k value is, you can obtain it with the help of your elbow point, which is like if you plot your number of clusters and the WCSS value, at one particular point you can find this elbow point, which is like the elbow, the sharp turn, you can see, right, the L-shaped turn. That point is actually a best number of clusters. That's what they are telling. Here you can see there is a curve or turn that is not that much. Okay, here you can see an elbow point, like an elbow. Okay, so that's what they are saying is, this elbow point graph will give you an elbow point. This value is going to be the best k value. So later on, what you can do is, you can train your algorithm with this k value. That will be actually a good one. Yeah, so we'll go and see a little hands-on about our elbow method and k-means, and then we'll go into the hyperparameter tuning techniques. So I'll start with a project which I'm having. So we'll be skipping some parts and directly jumping into the algorithm part. This is a mall customer data set Okay, this is the head, you can see, right? Okay, we need to rename, that's not required here. See here, we are having customer ID, gender, age, annual income and spending score. And what is the idea is they consider this as a unsupervised learning. There is not going to be any labeled data, which means you are not going to predict anything like annual income or a spending score or yes or no here. Your task is, it's a small customer data set, and what is the idea behind this? You want to segregate them. Okay, for example, if you find some customers who are spending a lot, okay, they have annual income of high like that, and some people have annual income low but they spend high, or some people have annual income high and they spend low like that. If you categorize your customers, then what you can do is you can go with respective advertisements for the mall. Okay, it's a shopping one, right? So you can go with specified coupon codes, gifts, etc., particularly to cover them. So you can do that task. So that's what the idea of this unsupervised learning project is. And yeah, we will be dropping some of the columns, and these are some of the informations, and yeah, for visualization is also available, but we will be focusing on our k-means clustering algorithm. Okay, this is where your algorithm is. Yeah, it's here. We'll go with that. So for using this k-means, we can import it from sklearn.cluster. You can import k-means, its algorithm, and as I told you earlier, we'll be using a for loop in the range of 1 to 10. So we'll be passing 11 to get till 10. And what I'll be doing is, every time I'm creating the model, okay, so the object is created with the number of clusters. Here is the parameter you need to pass, which is going to be the I value 1 till 10, and the init method here is going to be k-means plus, usually it is used, and we'll set a random state. And here, see here, I'm splitting the x value, which is, if I show you the x, it is nothing but the features. So what all the two features here it is selected is, I'm not going to consider some of the other columns. I'm just going to focus on these two, which is based on annual income and spending score. I'm going to cluster them. You can cluster with some more features also. Here I'm just taking care of these two only. So I'm turning them into an array. See here, 15, 15, 16, 39, 81, etc. will be here. That two columns are here. Okay, so their values are here. So that is now passed to fit. And if you ask me how to calculate the WCSS value, then what is done in the backend is, once you fit your model, I am appending it to a list. So what I am appending is, I am calling this k-means to pass out this inertia dot inertia underscore, and this inertia underscore will give you a value which is going to be your WCSS value. And every time this runs, I am just going to print for your observation. See here. So the first time this is the value, the second time this is your old value, comma the new value, WCSS value, and then this is the third value, like that. Okay, it is appending right to my list. So every time one value gets added, totally 10 value will be now in my list, which is going to be WCSS. And this is the distance. You can see it is keep on decreasing. And now what your task is, you need to plot it to find a elbow graph, right? So you can plot it with x-axis is going to be 1 to 10. You can use a range and then pass WCSS for y in plt.plot, and if I plot it, this is my elbow point graph I am getting. You know guys, you know how to pass these, etc. Okay, we are just getting from our inertia from k-means. Once we fit it, that will give me the WCSS value, and I am appending it to a list, and every time I am printing it so that you can see next time one value gets added, right? And this is the final values. And if I plot it, I need to find a elbow point here. So now I'll ask a question, what could be the best elbow point here? So I can see it is coming here. There is a turn, which is a slight turn, which is in the 3. And when I go for this place 5, there is actually a good elbow point is available. So here it is like confused between 3 and 5. I'll go with 5. It seems like 5 is actually really good as an elbow point. And you can see the elbow, right? So we need to pass like this. So that's a sharp turn. After that, it will be keep on decreasing. So we can choose the number of cluster k value as 5, and what I'm doing is, once again I'm creating a model with k value as 5 and setting the same thing, and I'm asking it to fit and predict the value of y. So here you can do it only one time, fit and predict it, the x value. So there is going to be no y here, right? This is unlabeled data, and what you can see is my output y is nothing but it has given 0, 1, 2, 3 and 4, which means that I'm having totally 5 classes here, which means 5 cluster has been created. I can also pass 3, which means 3 clusters will be created, only 0, 1, 2 will be available. So for each value or each row of x, it is giving to which cluster they belong to, either belonging to 0th cluster or first cluster or second cluster. So if I want to split them into 5, it will split them into 5 clusters. So based on that, you will be having 5 different classes. I'll turn them into, you can see these values will go with value counts, and in my data 81 data points belong to first cluster, 39 belongs to second cluster, 35 belongs to 0th cluster, 23 belongs to 4th, and 22 belongs to 3rd cluster. So if I visualize it using this plot, so you can see, so these are the centroid values and these are my 5 clusters which I am having, the customer group. So if you just plot it before this, when I go for the visualization, we'll see it. So this is actually a full project. We are just skipping some parts to just see about the algorithm. So we also have one clustering project where we will be seeing like this visualizations and all. So for example, the data is scattered like this, right? So you cannot manually go and select some people's here. So this is what the previous thing, annual income spending score, a graph, and you can see roughly I can tell this is a cluster, this is another one, this is another set of people. We have some extreme people here and here we have some. Okay, so that is what happened here, and with that values of the output I am passing it to a visualization purpose. See here, everything is a scatter plot. I am passing all the 5 points here with the label as what will be the y value as 0, 1, 2, 3 and 4, and if I go and get the cluster centers from my k-means object, I can get a plot like this. So we'll be doing it in our clustering project just to explain you about the algorithm. See here, so this is the centroid. So if I pass a new point, for example, if my new point is here, so it will calculate, okay, for example here, imagine, so if my new point, it will calculate the distance between, the algorithm will calculate this point's distance between this cluster, this guy and this guy. So whoever is near to him, for example, it seems like this is near to this, means it will belong to the red color group, or if it is near to this color, then it will belong to this group. So like that, the values will be splitted out. So the color green belongs to the first group, and then like 0th is green, red, that I have given. So you can set like this and get a visualization also. So that is what about our k-means clustering algorithm. We will be using it elaborately. We will see all the visualization detailedly when we go for a project, like 2-3 sessions afterwards. Continuing with the next one, which is hyperparameter tuning. So talking about hyperparameter tuning, hyperparameters are different parameter values that are used to control the learning process and have a significant effect on the performance of machine learning model. So before going into that, you know what is a parameter, right? We have seen about function. When we seen about function, we have defined some parameter and some arguments will be passed. And when we created, what we also did is we have also gone with some of the parameters which are optional, right? So you can give a default value there. So based on that default value, it will be usually setted. But if you want, you can go and optimize that too. If you want, you can change that value, give it, that will be taken into account. Like that, till now we have seen a lot of algorithms, and what they used to have is they have a lot of inside parameters. When you check the documentation we have gone through, right? So a lot of new names are available, lot of parameters for each algorithm is given. So how will you know best? Okay, because there are a lot of options available and you are just using one of the predefined or basic version and just using it. It's like what it is it's a common or generalized model. Okay, but for your particular data, what data you are having, what is actually the best fit? Okay, what will be the best parameter that you want to find out? That is what called as hyperparameter tuning, because whatever may be the algorithm, you can go and check the documentation. They will be having lot of parameters, and inside of it, if you scroll below and see it, they will be given that what are the parameters and what is the default which is available there. You can go and change it, and with that change your output will change. So you cannot just randomly go and do one by one manually, right? There are tools for it. So now listen, hyperparameters are different parameter value that are used to control the learning process, and they have a significant effect on the performance of the machine learning models. And an example of hyperparameter in the random forest algorithm is the number of estimator. Okay, so do you know what is the number of estimator? No, right? So you can check the documentation. What is the maximum depth and other criterions? And these parameters are tunable and can directly affect how your algorithm trains. So then hyperparameter optimization is nothing but the process of finding the right combination of hyperparameter value to achieve maximum performance on the data in a reasonable amount of time. So before going into that, I'll just show you some algorithm. Like we'll go with first a random forest classifier. I'm going into scikit-learn documentation. See here, these are the parameters it has been given. The number of estimators is 100, criterion is Guinea, max depth is given as none, and minimum sample split is 2, minimum sample leaf is 1. Okay, so you can see a lot of things here. So these are the default values. If you just scroll below, they will be giving you what is the number of estimators. It's an integer value, so default value is 100. Okay, so the default value of n estimators has been changed from 10 to 100 in the latest version. Fine. So talking about criterion, they have Gini, entropy and log loss. So the default is Gini, and this function is to measure the quality of a split. Okay, so you can check furthermore about the details they have given, like that maximum depth, minimal sample leaf. So what is the default value? You can obtain it. You can also know which type it is, integer or a float value. Based on that, we need to set some values and we can find out. And attributes, regarding the attributes, these are parameters, and talking about attributes, what's the estimator and the other features we are having. So you can go and alter it. You can learn furthermore in the documentation and find out to alter which parameters. For example, here we have seen some parameters, right? We can alter those. So how to alter it? How will you can manually go and set. For example, we have seen, right? So the maximum depth or the number of estimators is 100. I can set n underscore estimators equal to 200. Okay, it will run with 200. But in between you are having lot of values, and like that you have like max depth, you have a range of values, right? So you cannot go with here and there and manually do it. To achieve that, what we will be doing is we will be using something known as two tools are available. One is easy, another one is time consuming. We will see that one is grid search CV, another one is randomized search CV. So grid search will go one by one and do search on every grid which is given, and randomized search CV will do randomized search and give you quick results. And what is the CV is? CV is cross validation. Talking about cross validation, it is a resampling procedure used to evaluate machine learning model, and this method has a single parameter k, okay, which refers to the number of partitions given to the sample to be splitted into. So that they are often called as k-fold cross validation. The data is divided into training, validation and testing set to prevent data leaks. That's nothing but if you see this image, you can understand what is the 5-fold cross validation is. So the data is split into 5 parts, and in every iteration new set of data is passed so that you won't be losing your data. So all of your data will be utilized properly. It will prevent data leak. So that will happen in the cross validation. Going with the next one, which is starting with grid search CV. So this grid search works by trying every possible combination of the parameter you want to try in your model. You can give n number of combination. For example, how we will be passing is, we will be passing like this. Can you see this? I am passing the n underscore estimator value starting from 10, then 50, then 100, 200. You can go and give like 10 values, 20 values in this list, but it will consume a lot of time because it want to try all the possibilities here. For example, starting with n estimators as 10, max step none, then minimum sample split 2 and minimum sample leaf 1 for the 5 cross validation. CV I am setting 5. After that n value will change. These values will be constant. So once this is done, like that it will try every combinations available. So and it is going grid by grid. So all possible permutation of the hyperparameters for a particular model are used to build the model, and the performance of each model will be evaluated and the best performed one will be selected. Since grid search CV uses each and every combination to build and evaluate the model, this method is computationally a lot of expensive because it's going to take a lot of time. See here, it is going to go by one parameter and do cross validation. This, if you perform, you will be having, it will be taking a lot of time to complete based on your data. If your data set is small, like 1000 rows, then it can provide you answers really quickly based on your system CPU also. If you have a real world data which is like 1 lakh or 2 lakh rows, then it is going to take many hours to complete based on your capacity infrastructure you are having. So to achieve this, usually grid search CV, if you want, you can go, it's computationally expensive, but we'll prefer the next one, which is randomized search CV. So from sklearn.model selection, remember train to split, the same package we are using to import grid search CV, and this guy doesn't have any particular algorithm. So we'll be passing algorithm and this guy will perform all the combinations and give you the result. So from sklearn.ensemble, I am importing random forest classifier, and in the parameter grid I need to pass some parameters like this which I want to perform in the combination. So based on the documentation I can give for this random forest. When we go for another algorithm, for example if you go with linear regression, there the combination will be different, the parameters will be different, you need to check the documentation. And in here I am passing the n underscore estimators as these 4 values, and the maximum depth I am having none, then 10, 20, 30, it's an integer, right? So minimum sample split and minimum sample leaf I am setting. If I want, I can go and add further parameters too. This is just a dictionary. So I am passing these things to, when I build the object which is grid search CV, below that see here, and inside of it I am passing some parameters here. It is going to be the estimator is my algorithm, and here I am passing random forest classifier for this task, and the parameter grid will be the parameters, the dictionary I have created, I will be passing it. And we need to pass something known as scoring, which is going to what is the thing which need to be calculated. For example, it is going to perform all the combination, but how will it find the best algorithm? So it needs some evaluation, right? So we have seen accuracy score for classification, we will be seeing that in the end of this session also. So we are passing accuracy as the parameter to scoring. So based on that, who is having the high accuracy, he will be selected. That parameter will be given in the output. And the cross validation usually will go with 5. We have seen, right, what's the 5-fold cross validation is. Once you have it, we will be going with fitting our data, which is X train and Y train data. So once we fitted it, we can find, using that object, we can get dot best underscore params, and that will give me the best parameters. So the best parameters, if you get it, you can find which is the value, which is the good n underscore estimator value, which is the best combination in all these 4, that will be available. And if you go with best underscore, you can use it to create another algorithm, or you can directly get it from your best underscore estimator, that will give the best model, and you can use it to fit and then predict later. So this is how we use grid search CV. It will take a lot of time. We will go with randomized search. It is also going to be the same. Only instead of your random grid search CV, you will be passing randomized search CV. Same parameter, same scoring and same CV can be applied there also. That will be little bit fast, and we'll see how. So in randomized search CV, values for the different hyperparameters are picked up at random from this distribution you are giving. And randomized search CV is particularly useful when you have limited computational source and limited amount of time. If you want to explore and find the best values, you can use randomized search CV, and it provides a good balance between exploration and exploitation, and it helps you find reasonably good hyperparameters without any exhaustive search. So in your grid search CV, it will go every grid, but in randomized search CV, it will try to fit randomly based on your parameters you are passing and give you a result. which can be really good. And we will be mostly using randomized search CV. And see here also we are going to take from model selection. The parameters will be same for that particular algorithm, but here passing the same. Here we are passing our randomized search CV, and once you have it, you can go with your algorithm fit, and then we will be getting the best parameters and best estimator. Once you have it, you can fit with that your model. So we'll go and try hands-on with it. I'll try to create a simple project now as soon as possible. So I'll upload once again. We'll go with our hard data set. For this example, I'll import pandas as PD. We need a project because we'll be seeing about evaluation metrics also, so we'll see that. And data will be pd.read_csv. And we'll split our x and y values. X equal to data of data.drop, target, and the axis will be 1, y equal to data.target. And once I have it, I'll go with from sklearn dot model underscore selection import train test split. So x train, x test, y train, and y test will be train test split, x, y, and test size as 0.2, and random state will set it to 42. Yeah. Once I have it, I can directly choose some algorithm. For example, from sklearn dot ensemble, we'll import random forest classifier, since it's a classification problem. So I can directly create a model, okay, with random forest classifier and fit it, right? So fitting is the training, and I can go and predict it. Here I can see here it is giving me the parameters, right? So I can go with n underscore estimators as 200 can be set here. So I can go and do one by one. Instead of that, what we are going to do is we are going to use our tool, which can be your grid search CV or randomized search CV. So we can take it from sklearn dot model underscore selection. We'll import grid search CV, comma randomized search CV. So yeah, we'll create a parameter grid. Okay, so it will be a dictionary, so which should have the key name, which is going to be your parameters n underscore estimators. I'll set that values as, we'll go with 10, 30, 70, and then 100. Okay, so or else you can have different range also. Yeah, we'll change like 10, 50, 100, and 200. Okay, so we'll go with the maximum depth, and we'll go with a set it into none, and then some values 10, 30, and 50. So it's not stable, you can go and change it. So if you can run it one time and you can narrow it down and then find the best values, you can do that too. And yeah, here we'll go with some values. And then finally minimum samples leaf. So I'll set it to 1, 2, and 4. So we created this dictionary. So next what we are going to do is we'll create the algorithm, which is this is going to be, we'll go with randomized search. Okay, so when we go with our randomized search CV, what we are going to do is we'll call our randomized search, and I'll be passing parameters like the estimator is going to be your random forest classifier. and comma, we will be passing the parameter. Okay, so the param underscore distribution will be your parameter dictionary or your param grid. Comma, we'll go with our iteration value, we'll change that to 10, and also the scoring we'll set it to, this is accuracy, comma, CV I'll set it to 5, so I can go with this, and it has been done. So our next step is to just use this to fit our model, which is going to be randomized underscore search dot fit our x train and y train value, and let it fit. It will take some time. It's a randomized search CV only, but based on your data and your computation level, it will take some time and provide the results. And see here, it has been fitted as soon as possible. And what I can do is, now I can go and call randomized search. In that I can get the best underscore params, and this will give me the best combinations which is available. So the best combination they are giving is 200, then 2, then 1 minimum leaf, and max depth as 30. And you can use this inside your algorithm when you create it like this, or you can call your randomized search to give your best estimator dot best underscore estimator. So that will give you the best algorithm. So you can store it, for example, model equal to this one, and you can call model dot fit x train and y train value, and once you have it, you can call that to predict your x test value. So now if I want to give you a comparison, it is giving you the answers, but if you want to go with the verification like that, you can go with grid search CV also. It will do grid search. And yeah, that's all about your hyperparameter optimization and tuning. You can check the documentations, and based on that you can provide some values here that will be fitted, and the combinations based on it the best value will be given out. So now once you have everything, now you can just use your predefined algorithm, or you can modify their hyperparameter and get some values. So like that you can do everything, but ultimately you want to know which is best and which is not good. So for that task, what we will be simply doing is, we will be going with some of the evaluation techniques to learn how it works. So for each type of problem we have different set of values. So we'll go with starting with model evaluation. It is the process of using different evaluation metrics to understand a machine learning model's performance as well as its strengths and weaknesses. So the model evaluation is important to assess the efficacy of a model during the initial research phase. Okay, and also it plays a role in the model monitoring also. So for classification problems, we have accuracy score, precision, confusion matrix, etc. as a performance comparison tool which is available for you. When you go for regression problem, you will be dealing with error calculation can be done, mean absolute error, mean square error, root mean square error can also be done. So what is the math behind it, how it's happening, and how especially to use it, we'll see that now. Starting with accuracy score. So accuracy score we have already done, it's very simple, and accuracy score is a classification measure in machine learning that represent a percentage of correct predictions made by a model. And due to its simplicity in calculation and interpretation, the measure has found widespread use. Additionally, the performance of the model is quantified by a single number, right? So you can use it from sklearn.metrics, import accuracy score, and if you pass your original and predicted value, so the score will give you a decimal of 0 to 1, which is nothing but how much percent it is good. So if it's 0.7 means if you multiply it with 100, which is 70%, it is performing well. So usually we will be calculating like that. This accuracy score is doing nothing but you have your, see here, this is a classification problem. You have your original, this is predicted value, and you have your original values here in y test. So it just want to compare. So first one is 1, here also 1, next one is 1, here also 1. So 0, 0. So that's actually good. Like that it will correct. How many is correctly predicted? That will be in the correct marks, and how many is wrong, that will be given as wrong. So based on it, the score can be calculated. We'll do it from sklearn dot metrics, import accuracy score. So before passing the score, this is the original value. So the predicted value I will store here. Predicted equal to model.predict this value. So now I should pass the original and predicted one, which is going to be accuracy score. So the original value is y underscore test, and it's like the direct correction of questions. And see here how much it is performing. It is performing nearly 98% correct. So if I print it with 100, you can see this model is performing good because this model is best fitted. Can you see it? For example, I'll show you. Once again, I'll load the data set, and instead of going with our hyperparameter tuning, I'm just going to use this variable model which is not tuned. Okay, so now the variable model is having an algorithm which is not tuned, and I'm going to use it to. Here I'm not going to run this, I'll fit it with my original one. See here, original one, I'll predict the answers, we'll get the result, and we'll compare it now with the score. Okay, so it's actually performing good, but when you go with your, here it's fine. Okay, so yeah, I expected it will work before that, it will be working fine. But sometimes, or in most of the times, when you go with tuning your hyperparameters and check the score, you can see a huge improvement there because this is your generalized model. Okay, this model will be your generalized model, but when you go and fit it with your parameters, so that will give you some of the good parameters which can really show some improvement. You get the answer and compare it now. There's a slight difference, but still when you go and change it in this here, it's going to be a simple data set, but when you go with the real world data set, your hyperparameter tuning will help you to improve your score a lot more. So this is how you will compare your accuracy score for a classification problem. And then talking about classification report is another method, so you can get it from sklearn. So this classification report which will give you the value of what is the precision, what is the recall, what is F1, and what is support scores for the model. Okay, so you can find these terms hereafter. One is called as TN, which is true negative, which is the case was negative and predicted correctly as negative, which is true, and the negative is predicted as negative. True positive means the same case, true was positive and predicted as positive. False negative means it was positive but predicted wrongly as negative, and false positive means the case was negative but predicted as positive. So you can achieve this from sklearn.metrics. You can import classification report, and the report will be classification report, and you can pass your x train and y train value. So we'll pass it and see now. And also I just want to compare with another model. We'll go and import from sklearn.linear model, import logistic regression. So the model 2 will be logistic regression. I'll pass my model 2 dot fit x train and y train value, and model 2 dot predict x test, which will be the answer 2, right? So once I have this, I'll call the accuracy score, print accuracy score. I'm doing it in the single line. Accuracy score, I'll pass my original value and the new answer, which is answer 2, and we'll multiply the result with 100 and print it. So this should give me the final score, which is, see here, this algorithm is performing 78% logistic regression, but when you go with our random forest, you can see we are getting around 98%. Even without tuning the hyperparameter, with tuning hyperparameter, it is performing to this limit of 98%. So this is how we will compare which algorithm is good. If you go with tuning your logistic regression, you may get, or you may improve your score also. And I will see now about the classification report which we are talking from sklearn.metrics. Import classification report. and the report will be classification report here we'll be passing our original value, and we'll go with our original answer, first answer, and I'll print the report now. Okay, so what is the variable? Okay, it's prediction. So from our decision tree, it is given as prediction. We'll get the report, and this is what your precision score for 0 and for 1, the output you are having, the recall value, the F1 score and support score. And I can also print report 2, which is going to be, I'll call the report 2 as the same classification report, but for our later algorithm, which is going to be, we used our answer 2 variable, right? I'll print report 2 also. Using logistic regression, this is what the values, you can see how precise it is. So talking about precision, recall, F1 score and all, precision means the accuracy of positive prediction. How much positive predictions are available? Total positive divided by total positive plus false positive. And recall is what percent of the positive cases did you catch. So that will be total positive divided by total positive plus false negative. So like that we can get F1 score, etc. So if you want to visualize your true positive and true negative, false positive, false negative, if you want to understand this, I can show you with confusion matrix, that is also available. That will be your last in your classification problem. So what you'll do is, I'll go and do hands-on. You can import confusion matrix. I'll just show you from sklearn.metrics import confusion matrix. So matrix equal to confusion matrix, and that we need to pass our extrain value, it is our original values, which is y test, and the predicted value. I'll print matrix now, this variable, and you can understand what it is giving. So it is giving me these results. So if I want to understand this, okay, this is true positive, this is false positive, this is false negative, and this is false positive, which means that what is true positive, okay, or I can just show you with, you can import Seaborn as SNS. We know heat map, right? That is what it is. I can go and call SNS.heatmap, and I can pass this matrix inside, comma FMT equal to 0.1F. I'll set the annotation as true. You can see it is giving me the column names also. And see here, this is the values 102, 0, 3 and 100, which means that this is true positive, which means 0 is a positive case. 0 correctly predicted as 0 in 1 or 2 places. If you check your total length of your prediction, which is length of your y test, so that will be a value totally 205. Among this 205, your original your zeros is 105 and 1 is 100, and 100 correctly predicted as 100 in all the 100 places. 1 is predicted really correctly here, very accurately, but when you talk about 0, it has been predicted here, it has not been went wrong. Only 0 is predicted correctly as 0 in 1 or 2 places, and 0 wrongly predicted as 1 in 3 places. So that's what a confusion matrix is. If you want furthermore, I'll pass from our logistic regression, you can understand how bad it went in the logistic regression. So 71, 13, 31 and 90. So this algorithm total, what it has done is, so it correctly predicted 0 as 0 in 71 place, but it wrongly, the false positive is 13. Okay, 0 wrongly predicted given as 1 by your algorithm. In the answers, you are talking about the answer between these two. Okay, and 1 correctly predicted as 1 in 90 places, but in 31 places it went wrong. So that is what their difference. Okay, so this you can analyze from your confusion matrix or your classification report and simply accuracy score. And these are some of the metrics for your classification problem. And when we go for regression problem, once again we have 3 different things. One is error calculation, which is R squared error calculation. another one is mean absolute error, and the next one is mean squared error. So we don't have a regression problem right now, we haven't had the code, we need to start freshly. So what we'll do is we'll see these metrics, understand it, and when we go for a regression problem, we'll apply all these things when we see the regression project. Talking about R squared error, the R squared error, or simply called as R2 score, also known as the coefficient of determination, is a statistical measure used to assess the goodness of a fit of a regression model. So in the context of machine learning and statistics, it is often used to evaluate the performance of a regression model that makes prediction about a continuous outcome variable. And this is the formula 1 minus RSS by TSS. So what is here is RSS will be your yi minus y hat the whole square, which is what is the actual value minus the predicted value, summation of it. You know what is regression and how we calculate the error, right? In linear regression we have understood, we have a straight line. What is the distance between or difference between your original and predicted value? That is what given here. Okay, so sum of square of that. Okay, so we'll get the sum of square of it divided by the total sum of squares, which is yi minus y, the mean value of that variable, the whole square. So if you apply this formula, you will be getting your R square value. Y is the actual value, this y hat is given as the predicted value, and this y bar is going to be your mean value of that. So with these you can apply in this formula and get R squared value. So the output will be between a range of 0 to 1, and R squared error cannot be used for actually comparing to three models. There are, if you want to compare two regression model, there are different methods available. To achieve R squared error score, you can use from sklearn.metrics, you can import R2 underscore score, and you can pass your original and predicted values here. Talking about comparison, you can go and use mean squared error or mean absolute error. So what is this mean squared error? It is a commonly used metric to measure the quality of a predictive model in the regression problem. So it quantifies the average of square difference between your predicted and actual value. So all of these things will be using your what is the difference between original and predicted one. It will take the sum, and their formula is differing. Okay, so their output based on the formula will be different. So in other words, it calculates the average of squared error between model. See here, this is what we will be talking about, original value and their predicted value given here. And if you take a sum of their square, it is mean squared error. So if you have totally 100 samples divided by 100, what is your difference between your y value and predicted value? The whole square, summation of it. If you add everything and divide by 100, you will get mean squared error value. And we already know if every point passes exactly through this line, then the output will be 0, which means that it is actually a best fit, which is not possible. So if this value is less or closer to 0, that will be a good model. We can compare like that. In accuracy, it is different. It is around 100% to the scale of 100. Based on the percentage you can obtain. But here, you need to reduce the value nearer to 0. So LS value will be considered as a good model. And to do this, you can use from sklearn.metrics, import mean squared error, and you can pass your original and predicted value. Also, you can calculate root mean squared error. This is another one. This is nothing but in the mean squared error, if you take a root of it, square root of it, that will be root mean squared error. This is also used for calculations. So here in the same mean squared error, you can call numpy or math and call square root. So that will take the square root value and give you the result. So this is a simple example. This is your age and this is your output. And this is the prediction which has been given. What is the error? Original is 15, predicted is 26, error is 11. So like that they are calculating the error. Okay, and their square will be calculated. Okay, so the summation of this divided by n will be totally adding this divided by the total number of sample will be mean of squared error. And if you take a square root for it, you will be getting the square root of mean or mean square root mean squared error. Talking about the final one, which is going to be mean absolute error, it can also be used to compare different algorithms in regression. So it is a measure of average of residuals in the data set. So once again here also they are calculating the difference, but the formula and their application is different. So the mean absolute error is a valuable metric for assessing the accuracy of regression models. So it provides a straightforward and interpretable measure of the average magnitude of error in the same unit as target variable. So we'll be going with mean underscore absolute underscore error. So that will be helpful for us to calculate using this formula, which is going to be they are calculating the total number of error and like the sum of all absolute error. So it will calculate what's the absolute error is. You are not just absolute is not like you are not squaring it. Here, see here, we are getting this is your absolute error, this is your squared error. We are using square here and taking root of it. This is your absolute error. This value is taken and it will be summed. That divided by the total number of n value will give you the mean absolute error. You are not just squaring it. That's what the difference between your mean squared error and mean absolute error. And when you apply it, you can get a score which you can use for comparing your algorithms. So talking about regression, we have seen all these four. Mean absolute error, see the formula, not square inside. When you go for mean squared error, they are squaring it inside. When you go for root mean squared error, they are taking a square root for this mean squared error. When you go for R2 score, they are actually calculating the formula using your original value, predicted value at the mean value of that column. 1 minus that problem. So totally when you do, you can get or compare with any of these methods for your algorithm, for your different algorithms or your different hyperparameter or for your different features which you have selected. You can compare and find a best fit, best model for your data. So that's it about our model evaluation, and we have completed all the basic things which is required. So we'll be moving into our step 4 comfortably, which is going to be starting with projects. So we'll comfortably start it from the next session. We'll be seeing project. So we'll be starting with the classification, regression, and then clustering projects. Thank you.